This lesson teaches RYA Coastal Skipper and Yachtmaster students all they need to know about position, time, speed and distance. Fundamentally, there's only one way to define position, which is by bearing and distance from some charted or imaginary feature. For example, our position is 3 miles 075 degrees true from the isolated danger mark on Black Shoal. Or our position is 50 degrees north of the equator and 30 degrees west of the prime meridian. 50 degrees and 30 degrees are angular measurements. The equator and the prime meridian are imaginary lines on the Earth's surface. Obviously, we need to be able to define our position by latitude and longitude to a higher level of precision than a degree. So we use degrees and minutes, where there are 60 minutes in a degree and decimal parts of a minute. If we have to pass a position by latitude and longitude, there is a correct form. For example, 46 degrees 17.45 minutes north, 005 degrees 41.23 minutes west. Note that latitude is always given first. The level of precision depends upon the circumstances. Remember that 1 minute of latitude is 1 nautical mile, so you only need to give minutes to one decimal place to define your position to within 1/10 of a mile. Distance at sea is measured in nautical miles, where 1 nautical mile is approximately 1 minute of arc, measured along any meridian. At the first International Extraordinary Hydrographic Conference in Monaco in 1929, it was set at 1,852 meters. The nautical mile remains in use by sea and air navigators worldwide as opposed to, for example, kilometers, because of its convenience when working with charts. As you learned in the associated lesson on charts, most nautical charts use the Mercator projection, whose scale varies by latitude, but because 1 nautical mile is nearly equal to a minute of latitude on a chart, a distance measured with chart dividers can be roughly converted to nautical miles, using the chart's latitude scale. Nautical miles might be divided into decimal parts, for example 3.1 miles. Or, if the distance is less than 1 mile, the term cable is often used, where 1 cable is 1/10 of a nautical mile. So you might, for example, say, we are about 3 cables 075 degrees from the harbour wall. And remember that if you've measured your position using a bearing compass or GPS, and you are communicating it to another party, for example a coast guard, you need to convert from magnetic to true, and invert the bearing by adding or subtracting 180 degrees. Time is, of course, measured in hours, minutes and seconds. This means using base 60 arithmetic to perform time-based calculations, which is highly inconvenient, but unless you systematically work in decimal hours, which would probably confuse everybody else, you're stuck with it. In terms of quoting the time, you should always use the 24-hour clock, qualified by the time zone. Unfortunately, though, there are a number of ways of specifying the time zone, and this can lead to confusion. The ISO standard for defining time is as hours ahead plus or hours behind minus UT. Universal time, or UT, is the Universal Global Time Reference. To all intents and purposes, UT is the same as good old-fashioned GMT. The United Kingdom, Portugal, West Africa, etc. are all in time zone 0. Western Europe and West Central Africa are in time zone +1, etc. New York is time zone -5. Los Angeles is in time zone -8. So, if the time in London is 16:30, then it will be 17:30 in Paris and 11:30 in New York. If we ignore daylight saving time for now, we might say that the time in the UK is 16:30 UT. The time in Paris is 17:30 UT plus 1. The time in New York is 11:30 UT minus 5. The RYA training world is split into the Northern Territories at the top of this chart and the Southern Peninsula at the bottom. The Northern Territories are in time zone UT and mimic the United Kingdom. The Southern Peninsula is in time zone UT plus 1 and mimics the adjacent coast of continental Europe, France, Belgium, the Netherlands, etc. In the real world, this is called Central European Time, or CET, but the RYA refer to it as Southern Peninsula Time, or simply SP. Then, of course, there's daylight saving time. If you happened to be walking across Westminster Bridge on the evening of Christmas Day and looked up at Big Ben, you could say that the time was 1932 UT. That's because during the winter months in the UK, we use the UK's standard time zone, UT. However, from late spring until mid-autumn, the UK switches to British Summer Time, or BST, by advancing our clocks 1 hour. In other countries, this is known as Daylight Saving Time, or DST. Of course, clocks don't actually tell us that it's BST, we just kind of know, and in most circumstances it's not a problem. In the RYA world, we call Daylight Saving Time in the Northern Territories just that, or simply DST. In the Southern Peninsula, it's Southern Peninsula Daylight Saving Time, or SPDST. Times given for high and low water in almanacs are stated according to the time zone where the port is located, without adjustment for daylight saving time. See the first page of tide times for Namly Harbour on page 54 of the Training Almanac. Namly Harbour is in the Northern Peninsula, so the times of high and low water are given in UT. And, as it says in the top left-hand corner of the page, if we are operating in summer time, we need to add 1 hour in the non-shaded areas. For example, you can see that on April the 2nd there is a high water at 02:33 UT, which will be 03:33 on the Town Hall clock in Namly Harbour. It's just the same in the Southern Peninsula. On page 73 you can see that there is a high water at 05:18 UT plus 1, which will be 06:18 on the Town Hall clock in Hamilton. Unfortunately, though, almanacs don't comply with the normal convention on specifying time zones. Instead, they use the arcane maritime time zones in the form, for example, time zone minus 0100, to mean the same as UT plus 1. Frankly, it's crazy and leads to lots of confusion, but there it is. As it says in the box, to convert the times given to UT, you need to subtract 1 hour. So, the Northern Territories are in nautical time zone UT. In winter, the Town Hall clock will show the time in UT. In summer, it will show it in daylight saving time, which is UT plus 1. The Southern Peninsula is in nautical time zone minus 0100. In winter, the Town Hall clock will show the time in UT plus 1. In summer, it will show it in the Southern Peninsula as daylight saving time, which is UT plus 2. Please, don't shoot the messenger. You really need to get this right when navigating in one time zone using data presented for a different time zone. Just as in the English Channel, where tidal stream predictions are often based on the time of high water in Dover, irrespective of whether you're navigating off the English coast or off the French coast, In the RYA world, tidal stream predictions are based on the time of high water in Victoria, irrespective of whether you are navigating along the coast of the Northern Territories or Southern Peninsulas. You are told this on the training charts and in the Tidal Atlas, which appears on pages 13 to 25 of the Training Almanac. Let's imagine that you are planning a passage from Port Slade to Port Fitzroy via the Neptune Channel and Fiddler's Race. It's an area where the tidal streams run very strongly, and you need to get your predictions right. For example, on the 25th of June, we know that the tide sets fair in the Neptune Channel 3.5 hours before high water Victoria. But what time will this be on the Town Hall clock? There's a high water at 10:28 in Victoria, so within 2 minutes the tide will set fair at 0700 UT. However, we're in time zone UT+1 and we're on Southern Peninsula Daylight Saving Time, so that's 0900 on the Town Hall clock. Well, so much for defining position. What about finding, or more correctly, fixing our position? In the era before electronic navigation, the only way to fix your position was by measuring some combination or permutation of distance and bearing from a known geographic position, which might be a charted feature such as a lighthouse, or a calculated position such as a heavenly body's geographic position. A hand-bearing compass measures the bearing to a known geographic position, the inverse of which is your bearing from its position. Your ship's compass allows you to maintain a record of the course you have sailed from your origin, and your log records the distance. A depth sounder measures how far you are above the seabed, and a sextant allows you to measure the altitude of a heavenly body, which, in turn, enables you to calculate the distance to its geographic position. Radar can very accurately measure distance, and bearing less accurately. Of course, ancient mariners employed other cunning tricks, such as sampling the bottom with a piece of tallow in the hollow base of their lead line to see whether it were sand, shingle, shell, or mud. And sighting a land bird was often the first indication they had that they were nearing a coastline. And apparently Polynesian navigators and some fishermen of old were able to recognize an area in the ocean by its wave pattern and the type of sea life, animal and vegetable. Now you only have to glance at your chart plotter, and assuming that the GPS system is up and running, that you are putting your position to the correct map datum, and your charts are based on correct survey data, you can see exactly where you are. That's quite a lot of assumptions, and we'll be looking at GPS availability and accuracy later in the course. So let's forget GPS for now and examine a number of different ways to establish our position. Most simply, we could use our hand-bearing compass to measure the bearing to a number of different charted features. Remember to take bearings on things ahead or astern first, and things abeam last. Also, try to get the best possible spread. Imagine we are approaching this island and wish to find out how far off we are. We can take 3 bearings. There's a south cardinal on 283 degrees magnetic. An isolated danger mark on 273 degrees magnetic, and a west cardinal on 259 degrees magnetic. By plotting all 3, remembering to convert the bearings from magnetic to true, we can get a pretty good fix. Here we're assuming that magnetic variation is 6 degrees west. With more than 2 position lines, it's rare to get a common intersection, and the resulting triangle is often called a cocked hat. It's good practice to assume that you're in the corner of the cocked hat nearest to danger. Incidentally, ideally we would like to get a broader range of bearings, but sometimes beggars can't be choosers. When selecting objects to take bearings on, try to use things that are close rather than a long way away. Just 1 degree of error at 6 miles would place you at a cable, which is 1/10 of a nautical mile from your true position, whereas a 1 degree error at 0.6 miles is only 1/100th of a nautical mile, about 20 meters. Remember that when two charted features are in transit, you can plot a very precise position line. And you can combine sources of information in order to plot a fix. In this case, with the isolated danger mark and lighthouse in transit, a calculated height of tide of 2.8 meters, and a depth of water of 28.8 meters, we can plot a pretty good fix. Sectored lights can provide a useful position line, or a succession of position lines. For example, a vessel sailing southwest on a course to take her between Mutton Head and Gamp Holm will see the light on Johnson Point first turn from white to red and then disappear, as it is obscured by Cliptave Point. Each change can be plotted as a position line. GPS can give position in two ways, either by latitude and longitude, or, if you are navigating by waypoint, the bearing and distance to the waypoint. Note the abbreviations BTW for bearing to waypoint and DTW for distance to waypoint. Actually, it's good practice to plot a fix both ways, as it's all too easy to make a mistake plotting by latitude and longitude, especially if you're tired, in poor light, and when the fix is a long way from the latitude and longitude scales on the sides of the chart. Of course, waypoints don't have to be positioned on charted features, but they must be plotted carefully on the chart and checked again, and ideally checked again by another person, if they are critical to safe navigation. Your instructor was once sailing single-handed from Falmouth to the Solent. By the time he was approaching the Needles Channel, just after low water, it was blowing force 6 from the southwest and thick fog, with visibility less than 100 meters. He was very tired. He programmed a waypoint just south of Southwest Shingles Buoy into the GPS and was using it to plot regular fixes. When, by his reckoning, he was about a mile from the waypoint, and making nearly 8 knots over the ground, he noticed that the depth was rapidly decreasing, and he thought he could see breaking waves ahead. Very fortunately, a deep instinct told him there was something badly wrong, and he immediately put the helm down and clawed south. With too much sail up, the boat was heeled right over on a beam reach as he sailed through large breaking waves on the Needles Bridge, passing just east of the bridge westerly Cardinal Buoy. Had he continued on course, the outcome would have been very messy, probably involving lifeboats and helicopters. Analyzing the situation afterwards, he realized that he programmed the waypoint 1 minute, in other words 1 mile, north of his intended position. That's just 1 digit out. Had he plotted position by latitude and longitude as well, he'd have spotted his error miles away. Not only does this illustrate the danger of inputting an incorrect number and not cross-checking fixes by latitude, longitude, and bearing and distance to waypoint, but also that over-reliance on GPS can be extremely dangerous. So always try to validate a GPS fix by some entirely different means. In poor visibility, radar is a perfect solution, but if you don't have it, ask yourself whether the depth stacks up with your GPS position. In the pre-GPS era, a prudent skipper would have assumed that his or her fixes were inaccurate and would have either approached the Needles Channel very slowly, on a safer course, or headed somewhere else entirely. One useful shortcut is to program the center of a compass rose as a waypoint in your GPS. and then use a piece of paper to construct the ruler using the latitude scale. Note that you put 0 in the middle of the ruler. You can then place the 0 on your paper ruler next to the waypoint in the centre of the compass rose and swivel it round until it lines up with the bearing to waypoint on the opposite side of the rose to your position, and measure off the distance. This is much quicker and less error-prone than plotting by latitude and longitude, or even using a chart plotter and dividers. However, it can only be used on relatively large-scale Mercator charts, because as you learned in the lesson on charts, the scale varies with latitude.
The cross-track error grid is another tool for quickly plotting a GPS position as you navigate towards a waypoint. Here we've plotted one with 1 mile squares to help us navigate safely towards a waypoint on the leading lights into Whale Bay. With a GPS reading a cross-track error, XTE, of 0.3 miles to the left of our intended track, and a distance to waypoint, DTW, of 3.35 miles, we can quickly plot a position, and we would know that we must turn to starboard to bring ourselves back on track.
Contrast this with what might appear a simpler alternative. Imagine it's dark and you're in a fast motorboat. If the red line on this chart were your intended ground track from your 2100 fix to the waypoint, at 2110 you might be tempted to alter your course to 110 degrees to head directly for the waypoint. You might easily collide with the unlit yellow spherical buoy bang on your intended track. Not at all funny at 20 knots. If you regularly navigate into a harbour or estuary, and especially if you do so at speed, consider plotting a web like this on your chart. Again, you can plot a fix quickly without using any instruments. So, how often should you plot a fix? And how accurate does it have to be? Well, obviously, it depends on how close you are to danger and how fast you're going. In the middle of an ocean, thousands of miles from anywhere, once a day is sufficient. And in the days before GPS, you were doing well if you could fix your position by sextant within 50 miles from the deck of a small yacht in a seaway with only a few moments' break in the clouds. As you near land, the frequency of fixes needs to increase, perhaps once an hour in the middle of the English Channel, to an accuracy of within a couple of miles, reducing to every 15 minutes and half a mile as you approach within 10 miles of the coast, then down to 6 minutes and a quarter mile within 3 miles. Ultimately, if you're conducting pilotage in or out of a harbour, estuary or river, you might be fixing almost continuously. Remember, every fix must have the time and log reading written alongside it. If you are navigating to a waypoint, it's not a bad idea to enter the bearing and distance to the waypoint in the deck log every time you plot a fix. But don't get tempted to fall into the trap of failing to plot the fix on the chart, as it is only by doing this that you can see whether you are sailing into danger. If you don't have a GPS and you are out of sight of land or any other charted features that might enable us to plot a fix, then the fallback is to plot an estimated position, based on how far you've sailed since your last fix, based on the log reading then and now, and an estimate for leeway and tide. Tidal streams are covered in the next lesson, and we'll then progress on to working up estimated positions. Well done! You've completed the lesson on position, speed and distance.